what we have done is we've taken the general concept of a traction, and now we have taken that to derive our components of a generalized traction. And we wrote this in terms of a matrix form here, where we're looking at face. This is the face normal that we're acting on. So this would be an X face here. This would be a Z face here. This would be a Y face here. And direction. And so you'll note that we go face, 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 across, and then direction, 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 down. Now, why did I write it this way? Yes, this is equal to that because we're inside of a continuous body and we have to have preservation of equilibrium in this particular system. And so we have 6 components, 6 unknowns. Now this traction is our old formalized definition of some force acting on some area. And we simplified last time by taking this concept and defining a new term, and that was going to be stress as defined originally by Cauchy, where we're looking at the limit as area approaches 0 of force acting on an area. And so our system now changes to this. In this case, we want to preserve, oops, this needs to be Z. Where now we have an infinitesimal cube. See?
That says T-U-R-E. I can't read the first word letter.
Huh?
Right there. Right above the F over A.
Face.
Oh, that's his face.
Now, when we're looking at these systems, we said that we have, in this particular case, 3 equations, 3 linear equations, but we have 6 unknowns. So we have still a dilemma. How do we try to resolve this? And what we're going to do later on today is we're going to transform into a simpler system. We're going to take advantage of the ability to transform between coordinates into a coordinate system that will have only 3 values. 3 values, 3 unknowns, 3 equations. That will make life oh so much easier in trying to resolve this particular system. But before we do that, I want to make sure we understand some of the simple concepts of traction, of generalized stress. And so I want to work a problem, then I'm going to give you a challenge to make sure we can understand some of these problems. And the question that I'm going to ask is,
So I understand what you're doing. You're trying to simplify the matrix. So
good,
that we
I
can,
probably don't.
Okay. But anyways, my question is, we are allowed to equivalate or equate the sigma xz with sigma xz in the top right and bottom left corners.
Yes.
And you're, because over on the cube, the values, even though the vectors they represent different vectors on different sides of the cube are equivalent
They have to be equivalent
for us to be
to prevent that cube from rotating. And then as we shrunk the cube down, that remains
Yeah.
something that must be maintained.
But in
We
a
have
real-
to have these equivalent, those equivalent, those equivalent.
But in a real life situation, why can't we have more of one force on one side of the face of the cube and more on the other? And the,
If you're thinking, yeah, Tim, if you're thinking about an independent cube, absolutely. But this is a cube inside of this material body. So what we were trying to do is, remember, we had Godzilla over here that was causing a stress field. And we're trying to find a way to describe that stress field, realizing that it would vary from the greatest stress near where Godzilla was pushing, the least stress back in the corner in that system. And so we're trying to find a way to describe that. We started off with just a plane, but we had to do all these different orientations to the plane. We resolved that into a Cartesian coordinate system cube, if you will, to then resolve that we can move throughout our body. And now that's cumbersome, so we shrunk the cube down using the limit, and we have our definition for stress at a point.
We know it can't rotate because it's.
It cannot rotate within that material body. Okay?
yes.
So we're good? So now if we look at a system, let's go back and try to answer a very simple question. The question that I have for you is, if we have a lithospheric plate I now have a lithospheric plate. Let's say that we're going to use a simplified definition for lithosphere. Let's say that this is 150 kilometers thick. Let's make it 750 kilometers long. We can make it longer if you wish. And let's say that this is 250 kilometers across. My question to you is, if I gave you a density, let's say that the average density here is let's make it 2.5 grams per cubic centimeter. What is the stress acting at the base of this lithospheric plate?
Weight times height times gravity. Yeah, it's just a reverted.
So we want to, there's a couple of different ways we can approach it. We can approach it quickly, we can approach it simply, but there is a way that I like to look at it. It may be the long way around, but we want to try to figure out what type of mass do we have in this system, because we know F equals ma. Here. A, in this case, is a proxy for gravity, gravitational acceleration. Our mass here is a proxy of volume times density in our system. And so we want to see if we can simplify that down, look at this system as an F equals ma type solution to then resolve out what would the effective stress be if we were to use this simple definition. So how would we set this up? Well, the easiest way to do it, and since I'm old, I don't think very fast. If I look at this, I go, well, okay, the easiest way for me to do it is leave it in the CGS system, which I know drives you crazy. So I've got 750 times 10 to the 5th times 150 times 10 to the 5th times 250 times 10 to the 5th. That puts it in centimeters.
Oh, is that centimeters?
Yeah, they're 10 to the 5th centimeters per kilometer. So that's going to be my volume. I'm going to multiply that times my density. Then I'm going to divide by my area. So I'm going to divide by 750 times 10 to the 5th times, where is 250 times 10 to the 5th. And I need to add one other term. Gravity. Where am I going to put gravity? Up here. So I want to then come in G. So this is 2.5, this is 981. So what sort of value do you get? If we look at this thing, it solves out to rho GH. Which you knew from the beginning. So we get this relatively simple solution. We've been talking about it all along because we've used the concept of rho GZ all along. But as we walk through this process, we end up with a relatively simple solution. I see a bit of confusion from place to place. Yeah.
I don't understand why are we putting, I don't understand what's going in the denominator. The overall formula.
This is the
rho
area
Mhm.
of the base of the cube.
Certainly.
That's our area. This up here is going to be our force and our mass here. So that we come back to this solution, we divide by the area, we get our stress. Okay? And it turns out to be just rho GZ or rho GH in this particular simple solution. Does this make sense? This should be empowering because now we can ask all sorts of questions.
And then this equation, the rho GH, that gives you the stress.
That is going to be the stress acting at the base of that lithospheric plate.
But will we not be using that 9x9, 3x3?
Not yet,
Okay.
because this is in balance and it is simply a passive system. Now, when we look at this, there are lots of different ways of asking questions here. We have an exam coming up on the 30th, Halloween. I would anticipate there being some questions along this line. And what we might do is, instead of having a nice rectangular system, what if we had a thrust system?
Different graded, different pressures at different points.
Yeah, we're going to have variations of stress. If we put this thing into the third dimension, we can start thinking about what would stress be at various points of our thrust system. We could say that the stress here is some given value, and we might even add a bit of complexity. We might put a ramp in here and say, what's the stress at the ramp? Which would be an intriguing question to ask. Because you're going to have a vertical, we would have to assume a horizontal, and we're going to then need to think about this system here.
So say you're trying to solve for like pore pressure in a reservoir, and you know you have numerous rock layers. Do you just continuously change your densities and just keep summing heights?
You would just sum, yeah, you would just do it as a summation
Okay.
in the system.
Does that become with the grade? Like typically they give like gradients,
Mhm.
so just like hey, just use this.
And then you have to think about what does the edge of the compartment look like? What's the fluid continuity? Do I have any stress drops within the fluid? Is this a perfect compartmentalized reservoir? Is it a partially leaky reservoir? What does my pressure head do? Because when we think about reservoir compartments, the pressure head moves much more quickly than the fluid does.
Right.
And so you've got an energy balance, you've got an interesting equilibrium problem there. And so it's a little bit more dynamic than what we're thinking here. But perfect question. Okay, does this make sense?
Can you do a problem where we would have to use that 3x3?
We will, we're getting ready to. Now, in this setting, I'm going to give you a challenge. Work in groups of 2 or 3 here. And this morning, what I